I'd like to introduce you today to the nomenclature of alkenes, or the way that we name them. Just as a reminder, remember that alkenes are hydrocarbons that contain a carbon-carbon double bond. This is the simplest of alkenes, ethene or ethylene, so you have to have two carbons in the molecule at a minimum in order to have a carbon-carbon double bond, obviously. And again, to remind you that a double bond is really made up of two bonds, and it's two different types of bonds. First, we have the sigma bond, which is made up from the overlap of two sp2 hybridized orbitals. And then we have the pi bond, which is made up of overlap between the two unhybridized p orbitals. A double bond, again, is composed of a sigma bond and a pi bond. Let's review a little bit about the molecular formulas. I've shown you this formula before for alkanes several times, and the general formula, remember, is CnH2n plus 2. I also told you that the general formula for an alkene is CnH2n, or in other words, you could say it's CnH2n plus 2 minus 2p, where p stands for the number of double bonds. In other words, every time you make a double bond, you take away two hydrogens. Remember that CnH2n is the same general formula for a cycloalkane. Or in other words, you could say CnH2n plus 2 minus 2r, where r is the number of rings. Because remember, every time you go from an acyclic hydrocarbon to a cyclic hydrocarbon, you have to form a bond between two carbons to close that ring, and every time you do that, you also lose two hydrogens. So the general formula for a cycloalkene could be CnH2n plus 2 minus 2p, the number of double bonds, minus 2r, where p is the number of double bonds and r is the number of rings. You could make a more general formula, CnH2n plus 2 minus 2 du. And what does du stand for? Du is degrees of unsaturation. So for every pi bond, you have 1 degree of unsaturation, and for every ring, you have 1 degree of unsaturation. Let's look at the way that we name alkenes, and you're going to see that it's very similar to the way that we named alkanes. First, you're going to find the longest carbon chain, just like you did when you named the alkanes. You're going to number the carbons so that the double bond gets the lowest possible number. If you have substituents, you're going to put the name of the substituents before the parent, and the parent, remember, is what identifies the longest number of continuous carbons. You're going to include a number for the locant, which indicates the position of the substituent. Let's look at a few examples. This is our very simplest alkene, and I've already told you the name of this. This is called ethene or ethylene. You'll hardly ever see anybody call it ethene. Ethylene is more commonly used. What I want you to notice is that going from ethane to ethene, we've changed the ane for alkane to ene for alkene. That indicates to you that there is a double bond. Here we have propene, or more commonly known as propylene. And in this situation, both of these molecules that I'm showing you here are the same. They're just different orientations of the same molecule. So in both of these cases, I do not have to indicate where the double bond is, because there's only one place where it could be. But if we have a situation like this, we have 4 carbons, 1 double bond in each of these molecules, but these molecules are different. These are constitutional isomers. They're both butene, but they're not the same butene. So I have to include the number that tells you where that double bond is located. On the left, I have 1 butene. You might also see this referred to as but1ene, and either one of those is correct. I'm going to go with the 1-butene nomenclature because that's what your book uses. Our second compound on the right, we would call 2-butene or but2ene. Again, either one of those would be correct. If I have something like this, I have 6 carbons, so that's obviously going to be a hexene. And there are multiple positions where that double bond could be located, so I have to tell you where that double bond is at. So I number my carbon chain, starting from the end closest to the double bond. So this molecule would be called 2-hexene. Here I have a situation where I've numbered the carbons in the longest continuous chain from opposite directions. And you'll notice that in each of these cases, my locant, or my position for my double bond, is the same. But the position for the substituent, the methyl group, is different, depending on the direction that I number the chain from. When you run across a situation like this, and the double bonds are at equivalent positions, either way that you number, you're going to choose the direction that gives you the smallest locant for your substituent. So the correct name for this compound would be 2-methyl-3-hexene, not 5-methyl-3-hexene. Here we have a situation where I'm numbering a heptene, and it's a substituted heptene, same molecule, numbering from opposite directions. And in this situation, I get 2 different numbers for the location of my double bond. You'll see that I have either a 3-heptene or a 5-heptene. And as a result, I get 2 different locants for my substituents as well. So who's going to win? It turns out when the double bonds are not in equivalent positions, when you number from opposite directions, you're going to choose the direction that results in the smallest locant for the double bond. In other words, the double bond takes priority over the alkyl substituent. We're going to come across situations in this class where you have multiple functional groups, and there is a priority list for functional groups. And we'll talk about that a little bit later when we start looking at more and more complicated molecules that have multiple functional groups. Then you have to decide which of those functional groups takes priority. But just for our purposes for the moment, just remember that the double bond is going to take priority over the alkyl substituent. And that also applies to halogens as well. Double bond takes priority over the halogen substituents. So my name here is going to be 5-methyl-3-heptene. I want to go with the 3-heptene because that's the smallest locant for the double bond. It's not going to be called 3-methyl-5-heptene. If you have more than one double bond, you can use the suffixes di, tri, and tetra after the parent or the root and before the ene. So this compound I'm showing you here is 2,4-hexadiene. In this situation, it doesn't matter which direction that I number from. My locants for my double bond will still be 2 and 4. But here's a situation where it does make a difference which direction that I number from. Numbering from the left gives us 3,5-hexadiene. Alternatively, if I start from the right, I get 1,3-hexadiene. I'm going to choose the name that gives me the lowest locants for my double bonds. So this is 1,3-hexadiene. Here we have a situation where we have a substituent. Again, we have a diene. We have 7 carbons. This would be a heptadiene. I'm going to number in the direction that gives me the smallest locants for my double bonds, or closest to the end with the first double bond. So my locants for my dienes, or my alkenes, are going to be 1 and 3. So the name of this molecule is 5-methyl-1,3-heptadiene, not 3-methyl-4,6-heptadiene.